Hello everyone. In this video you'll be learning how ethers react, how they are treated with a strong acid and also result in cleavage of the ether bond and giving rise to an alcohol or an alkyl halide. Ethers are very unreactive, but when they are treated with a strong acid, you'll see some of the different products that are formed. So in this video, I have tried to solve problems which are more representatives of almost any ether that you could find, how they would react and the mechanism of the reaction. Please understand each step and watch the whole full video of how the problem is solved, and make sure that you understand the mechanisms. Once you understand the mechanism of how ethers react, everything is in this video is very simple and fun to watch and exercise with it. Okay, thank you. Okay, let's go ahead and try to solve this problem. The problem here is there are three different ethers, and the question is, give two counterparts how you would synthesize these ethers. As you know, ethers are synthesized by Williamson Ether Synthesis. For that you need an alkoxide, appropriate alkoxide, and you also need an alkyl halide. That means, for example, if you are trying to see this isopropyl ethyl ether, the way you will synthesize is by breaking it down either here or here. If you cut it here, the alkoxide would be the isopropyl oxide, but if you cut it right here, it will be the ethyl oxide. Ethoxide would be the counterpart. As a general strategy, you always need to have the alkyl halide as a primary, maximum as a secondary. That means the alkyl halide should be a very unsubstituted, less bulky counterpart. Let me do this now. For example, if I do here, if I cut it right here, I'm suggesting that the alkyl halide, for example, a bromide, plus an alkoxide like this. This would not be the best combination of making that ether, even though it can attack here by substitution reaction. You ought to have the primary alkyl halide the other way. For example, if you just cut it the other way, if I cut this on this side, that means the alkyl halide would be the bromide right there, plus the alkoxide would be on the isopropyl oxide. So this is the best combination, where you have a primary alkyl halide and you have the alkoxide. So that would be a good combination. This would not be very favorable. This is favorable. For example, in this one, let me cut right this, and I would get, by cutting it right there, the alkox, for example, the chloride, let's use a chloride alkyl halide, plus the alkoxide would be the propyl alkoxide. Here I'm creating a secondary alkyl halide, but I have a chance, if I cut it the other way, this way, I would get an alkoxide here and an alkyl halide, which is a primary alkyl halide, which is a chloride one. This is primary. So this is a very good reaction counterpart for that ether formation. This is a cyclohexyl propyl ether. So all of these are ethers. And on the last one, it is obvious you can cut it either way, because both of them would give you a primary alkyl halide. So if I cut it right here, this would be CH3, CH2, Br, and the alkoxide would be a propyl alkoxide. So I don't see much of a difference if you were to cut it from here based on whatever you have as an availability. If you cut it that way, it would be CH3, CH2, alkoxide. No, that is, yes, an alkoxide, and the alkyl bromide would be this. So basically, in ether synthesis, the most important thing to remember would be that you want to have the alkyl halide or the electrophile to be a primary or less crowded alkyl halide, and the ether is what you could afford, I mean what you have in that case. So first make sure that your alkyl halide is not secondary. If it's possible, you want it to be primary. That's all the strategy you would be following in ether synthesis. So we'll continue more. Go ahead and solve this problem as well. So this is a phenyl ether. It's an ether compound, but it's asking you why this cannot be synthesized with Williamson Ether Synthesis. So it says why it doesn't work with Williamson Ether Synthesis. So this cannot be done by Williamson Ether Synthesis. Why? It's asking you to explain why you wouldn't do this by SN2 reaction on this compound right there. So let's see the done earlier. If you just cut here, you'll have an alkyl, not an alkyl actually, an aromatic halide. Let's say it's a chloride. You would have a T-butoxide bulky base, not a profile. So these are both not proper for synthesis. First of all, you cannot do no SN2 reaction on aromatic halides, Or, in other words, hybridized carbons or sp2 hybridized carbon, they don't do SN2 reaction. A nucleophile cannot attack right there and replace it. That doesn't happen. This is a very important concept in organic chemistry to learn that you don't do substitution, nucleophilic substitution on aromatic halide of whatsoever. So also is not a good nucleophile. This is bulky base. So it acts more as a bulky base than acting as a nucleophile. So in both cases, it fails that we cannot synthesize this with ordinary Williamson ether synthesis. So the synthesis would be a different one, which may not be covered in this. If you cut it right there, what you'd get would be a phenoxide, which acts as a nucleophile, and a tertiary halide, let's say X or chloride. You have CH3, CH3, CH3. There is no, in this case, the phenoxide because it's resonance stabilized, this negative charge is not available to attack that. So this is not a good nucleophile. This is aromatic alkoxide, not a good nucleophile. And here, this one, you cannot do SN2 reaction on a tertiary carbocation a tertiary halide. This is tertiary. In the previous one, I have mentioned that your alkyl halide with Williamson Ether Synthesis should be at least a primary alkyl halide. So this will not be good halide. So this is tertiary. You need tertiary is not a good counterpart as Williamson Ether Synthesis. So in both cases, it fails that you will not be able to synthesize this compound with Williamson Ether Synthesis for both these chemical reasons. So as organic chemists, you want to explain why that cannot be done using a regular Williamson Ether Synthesis. So this is only possible when you understand mechanisms very well, that you can come up with such explanation. Okay, we'll continue on more. I have two questions here on the board, and they are both ethers. So the question for this is, what are the products of this reaction? Here you have a cyclohexyl ether and also a tert-butyl propyl ether. In both cases, they are treated with a strong acid. Whenever an ether is treated with a strong acid, the consequences are that the ether bond, the carbon-oxygen bond, would break because it's a very strong acid, and it results in the protonation of that oxygen, and it would split into two components. So in most cases, you'd be given, or you would be asked, 1 mole of hydrobromic acid or any strong acid as 1 mole or 2 moles. So whenever you are given 2 moles, it further protonates. So we'll see how that goes. But when you have 1 mole of the strong acid, the first step is the protonation of the oxygen. In that case, it becomes more labile or easy to leave. So initially, that oxygen, lone pair of oxygen, would get protonated. So if I just put it as a mechanism, it would be tert-butyl C here, OH. Now H is provided from the strong acid, gets protonated, CH2, CH2, CH3. So this is what initially would happen. And remember, Br minus is in the reaction itself. So it could just happen as SN2 or SN1, for example. If you just do a bromide coming and attack this carbon, this would leave as an alcohol. Or it could break the other way. So both ways are possible. So for this one, for the initial one, if Br minus as a nucleophile acts on this carbon, you'd lose this whole thing as a neutral alcohol. So you'd get CH3, 3 alcohol, T-butanol, and also the alkyl halide, Br, CH2, CH2, CH3. This is in one case where the Br minus attacks that primary carbon. But it is also possible that it could leave as the alcohol, and a carbocation would be formed here. That means if this leaves and the other one is formed as an alcohol, you could also result in making CH3, CH2, CH2OH. The alcohol would be now the propanol alcohol, and the alkyl bromide would be Br, CH3, CH3 on the other side. So this side, it is acting as SN2 reaction of the Br minus, but the other side should first leave and act as SN1. So the SN1 product, the SN2 product is this one, or the SN1 product is the lower ones. So it's a complicated mixture of compounds you see. But when you are given, for example, in this case, so the 1 mole always gives an alcohol and also the alkyl halide or any nucleophile that is present. But when you have 2 moles of the hydrobromic acid or the strong acid, you get 1 product. We'll see that. So the first thing is the protonation of this. That would give me the same as what we have, OH as a plus, and a good leaving group now, 1 would leave. So if, as it is now, let's say this leaves like that, and it gives you an alcohol and a carbocation, which the Br minus would come and attack that, and you'd have obviously the alcohol and also the bromide. So that's what you get, but that is from 1 mole of the hydrobromic acid. But the next, another mole of the HBr would again, this is another HBr, so this alcohol now gets protonated. Remember, the ether was protonated first and resulted in a good leaving group. You have the cyclohexanol and now the alkyl bromide. But in the second mole of the hydrobromic acid, which is a strong acid, would protonate that alcohol. That alcohol makes a good leaving group, OH2 plus, from getting 1 proton from here. Remember, you have Br minus there. So if it is going through a carbocation, secondary carbocation, and Br minus is still floating around, attacks that, now it forms the cyclohexyl bromide. At the end of the day, you got 2 moles of cyclohexyl bromide. So the result of 2 moles of HBr protonation would result, actually the final result of that is you get 2 moles of cyclohexyl bromide. When it is 1 mole, you get the alcohol, a mixture of the alcohol and the bromide. But when you are given 2 moles of the strong acid, everything would go to, finally would go to 2 moles of the cyclohexyl bromide. This is something you need to know. When an ether is subjected to a strong acid, it would start to cleave and start doing hydration, and then combines to make 2 moles of the alkyl halide. Okay, we'll continue more on this. Here we are asked to show a stepwise mechanism of this cyclic ether of 5-member ring when it's treated with 2 moles of hydroiodic acid, very strong acid, to give this diiodo open chain compound. How do you arrive to that compound? So it is for us to show the mechanism of treatment of this ether, cyclic ether, into that open chain system. So initially, always, the initial step is the protonation of the oxygen with 1 equivalent of the proton. That means you'd have initial protonation that would give you H and a plus. Obviously, you would have that. So after you have this initial protonation, of course, the iodine minus is around. First, what happens is this is not very stable, so it would just start to leave. That means it would break either here or there. But since you would be breaking it and get a carbocation, which is tertiary, this breaks like this. When that bond breaks, you'd end up having this carbocation and also an OH here. So that's what you get at this point. That is a tertiary carbocation, and you have an alcohol. So this is just a neutralization of that. So now the I minus, the iodide nucleophile, it is a very strong nucleophile. Once it gets a carbocation, it comes and attacks that carbon to form a bond. So it will be OH, an alcohol one side, and an iodo compound at this position. Now you see why that iodo is right there, but you have an iodine in this. So you just used 1 mole of hydroiodic acid. Now the other HI, 1 mole of that, protonation of that alcohol would pick up that proton, and it gets transformed into a good living group, OH2 plus, and an iodo compound right there, which is the same. Now it doesn't form a carbocation by leaving water because it's a primary at that point, but the iodine minus would do an SN2 reaction. Here the iodine is doing SN1 reaction, but in the second step, since this carbon is a primary, the iodide attacks that and this leaves. But this mechanism right here for this one is SN2. What happens is finally you would get your product. That is the product, which is this. So it is a sequential SN1 and SN2 reaction to give this final product, because you are using 2 equivalents of a very strong hydroiodic acid. By the way, hydroiodic is much more strong acid than hydrobromic acid. So it immediately results in the cleavage of the ether group. So always when a strong acid is given to or reacting with an ether or cyclic ether or open chain ether, the oxygen would get protonate easily and become more easy to leave. Okay, we'll continue with one more question on the ethers. Okay, let's solve this final problem in the ethers, and we'll continue with another video on epoxides, the reaction of epoxides. But this is just one final mechanism reaction for the ether reaction with the strong acid. The strong acid here is trifluoroacetic acid. It's an organic acid, completely substituted fluorides. This is the molecular formula, CF3CO2H. It is called trifluoroacetic acid. I will just write it down. Trifluoroacetic acid. So when you treat, obviously, the ether, this is a cyclohexyl and a tert-butyl ether, and you are forming here one alkene and one alcohol here. And you are given only one equivalent of trifluoroacetic acid. And the question is just to give the mechanism for this, how those are formed. As I said, this trifluoroacetic acid has an acid group where the initial ether, that's always what ether does, gets a proton and gets protonated. So the mechanism is protonation with a strong acid. So you will convert that into this group where you have the ether bond, or the oxygen gets protonated, and you have this group right there. Now, in this case, the mechanism shows you that the alcohol is formed and there is an alkene. So obviously, this compound, this intermediate, goes by neutralizing and breaking the bond into that, immediately giving us out the alcohol, which is immediately obvious to us That is how that is formed, by just breaking that bond. But you have a carbocation, a tertiary carbocation that's formed, which is a t-butyl cation. T-butyl cation is very stable. Now you have it like that. But here you see it is an alkene, so it undergoes an E1 mechanism. So for this one, with E1 mechanism, you can form that alkene to get to that. What happens is the trifluoroacetate, or the conjugate base, can abstract one of the proton, beta elimination. And that means you have a CO2 minus conjugate base as a base. That is sufficient enough to just abstract that, which is this base, O minus CF3. It is from this, but it doesn't have proton. Now, one of the hydrogens from here, for example, if you have this CH like that, and this is CH2, this electrons would pick up that proton, that is like that, and then this would be satisfied. That makes a double bond. So it gives to this product. So what happens is initial protonation of the ether, which is always true if you have a strong acid like trifluoroacetic acid, hydrobromic acid, hydroiodic acid. Once it gets protonated, it's easy to break that bond. So it breaks by forming an alcohol one side, and in this case, a stable tertiary carbocation from the other end. But the tertiary carbocation would not be staying there while you have a very weak, even though a very weak base. By doing beta elimination, meaning that it takes that proton, it's called beta elimination, meaning that the beta hydrogen is taken away. This is the alpha carbon, this is the beta carbon. So this is beta, this is alpha. So by just losing one of the, all are equivalent, losing one of the beta hydrogens will make that double bond. An alkene is formed from E1 mechanism. The E1 makes the alkene. So this is basically what happens when ether is treated with a strong acid such as trifluoroacetic acid. So the next series of videos for me would be just to give you also problems related to epoxides. Please follow those videos as well, because that would give a detailed problem solving also of epoxide reactions. So far what we have done in this video was ether reactions. Okay, thank you.